Hi, I am Dr.A.P.SUDHA. Today we will see about arithmetic circuits. Arithmetic circuit is a type of combinational circuit that performs arithmetic operations on binary numbers. So arithmetic operations means addition, subtraction, increment, decrement, like that. So combinational circuits mean it consists of number of logic gates connected together to form a final output. Circuits that can add and subtract the binary numbers can be constructed by combining different logic gates. Output of the combinational circuit at any instant of time depends only on the present inputs. So it does not depend on the previous inputs. So these arithmetic circuits used in computers, calculators and digital systems. So if we want to design a logic circuit, so there are different ways. First, if a logic circuit is given, we can form a Boolean equation from the logic circuit, then we can form a truth table. Otherwise, if the Boolean expression is given, we can form a logic circuit and then truth table. But in most of the cases, to design a digital circuit, we have to start from truth table. Truth table. Next, from the truth table, we have to achieve Boolean expression. From the Boolean expression, we have to achieve logic circuit. From the truth table to the logic circuit, we have to achieve means we have to follow two methods. One is sum of products, another one is product of sum. Sum of products means that expression is the logical sum of number of logical product of input variables. So for example, y is equal to a bar b c bar plus a b c bar. So this a bar b c bar is a product term, and again another product term is a b c bar. These two product terms are summed together to form a sum of products. Okay, next method is product of sum. So the product of sum means that expression is the logical multiplication of number of logical sum of input variables. Example, y is equal to a bar plus b plus c bar into a plus b bar plus c bar. So here a bar plus b plus c bar is a sum term. Another sum term is a plus b bar plus c bar. So these two sums are logically multiplied to give a product of sum expression. So in arithmetic circuits, the two important circuits are adder and subtractor. In the adder, we have two different types. One is off adder, another one is full adder. First we will see about off adder. So off adder means it's nothing but if you want to add two bits, 0 plus 1 is 1. So if you want to add 1 plus 1 means 1 plus 1 is 0, 1. So we know the binary addition. In the simple binary addition, 0 plus 0 is 1. Sorry, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is, sum is 0 with carry 1. So this is the basic binary addition rules. So if you add 0 plus 1, if you add 0 plus 1, the answer is 1. If you add 1 plus 1, the answer is 0 with carry 1. So off adder is a logic circuit which is used to add two bits. So there are two inputs, A and B, and two outputs, sum and carry. So this shows the block diagram of off adder where there are two inputs A, B and two outputs, sum and carry. So we have to design the off adder circuit starting from truth table. So since we are having two inputs, total number of possible combinations is 4 because we know the formula. The total number of possible combinations, input combinations is 2 power n, where n is the number of inputs. So since there are two inputs, 2 power 2 is 4 combinations. So 0, 0, 0, 0, 1, 1, 0, 1, 1. So by applying the basic binary addition, we form the sum and carry output. We know that 0 plus 0 is sum is 0, carry is 0. So 0 plus 1 is sum is 1, carry is 0. 1 plus 0 is sum is 1, carry is 0. 1 plus 1 is sum is 0, carry is 1. So we have formed the truth table for an half adder circuit. From the truth table, we have to write the product of some expression. So product of some expression means sum of product expression. Sum of product expression means we have to select the rows which has I output. So in this case, we are having two outputs which has I. That means two rows which has I outputs. So for the first output, the product term is A is equal to 0 and B is equal to 1. So A is equal to 0 means we have to take A bar, B is equal to 1 means we have to take the as it is. So the product term consists of the number of variables. That variables may be in the complement form or normal form. So for the second output, so A is equal to 1, so we will take the A as normal form, and since B is equal to 0, we have to take B bar. So A bar plus B plus A bar A B bar is equal to A XOR B, which forms the XOR gate expression. So now we will write the sum of products for carry. So for carry, the last row only takes the I output. So the product term is carry is equal to AB. So if you see the sum expression, it is equivalent to XOR gate, and if you see the carry output, it is equivalent to AND gate. So by using these two expressions, that is the sum of product expressions, we can implement these expressions into a logic circuit. So sum expression means A XOR B. So we have to A and B is given to an input of an XOR gate. So that output is taken as S is equal to A XOR B, and to form a carry output, we have the same inputs are given to an AND gate, and the output is taken as carry is equal to AB. So this is the logic circuit for an half adder. Okay. Next we will go for full adder. So what is full adder means? Full adder is a logic circuit which is used to add 3 bits. So the 3 bits are A, B and C. So here we have taken A and B are 2 inputs, that is significant inputs, and the third input C is taken as a carry input generated by the previous lower significant inputs. For example, so if you want to add these number, 1 plus 1 we know that 0, carry is 1. So 1 plus 1 is 10, carry is 1. Okay. So in the LSB, that is if you see this point, we are adding only 2 bits. So to add these 2 bits, it is enough if we are using half adder. So by adding these 2 bits, a carry is generated and pass over to the next higher position. So to add these 3 bits, we need another circuit which is named as full adder. So full adder is a logic circuit which is used to add 3 bits. The 0 and 1 is a normal AB bits, that is AB significant bits, and this 1 is a carry bit. So we are adding 3 inputs. So this shows the full adder block diagram. So it has 3 inputs and the outputs are sum and carry. So let us take the truth table. So we know that there are 3 inputs. So total number of possible combinations is 2 power 3, 8. So there are 8 combinations are there. So by writing the 8 combinations, we have to find the sum and carry output. So we have to apply the normal binary addition rule. So for the first combination, the sum is 0 and the carry is 0. For the second combination, sum 1, carry 0. For third combination, sum 1, carry 0. So similarly, for the last combination, sum is 1 and carry is 1. So after finding this truth table, we have to convert this truth table to the sum of product terms. For choosing these or for converting this truth table to sum of product form, we have to select the rows which has I outputs. So these are the rows which has I output. So for the second row, the product term is A bar, B bar, C bar. So for the third output, the product term is A bar, B, C bar. For the fifth row, A, B bar, C bar, and for the last row, the product term is A, B, C. So after writing the sum of product expression, we have to simplify this to form a simple Boolean expression. So we have to select these two terms. So in these two terms, C bar is common. So we can write it as A bar B plus A B bar into C bar plus, if you group this, we will get, in both the equations, C is common. So A bar B bar plus AB into C. So we know that A bar B plus AB bar is the Boolean expression or Boolean equation for XOR gate. So this can be written as A XOR B into C bar plus A bar B bar plus AB into C is the Boolean equation for XOR gate. So we have to write like this. So if you assume this A XOR B as a single term, let M is equal to A XOR B. So next, so if you take the complement of M, it is equal to A XOR B, the whole bar. Substituting these two values in the above equation, we get M C bar plus M bar C. So if we are getting like this, means M C bar plus M bar C is again a output for XOR gate in terms of M and C inputs. So we can write it as M XOR C, where M is the A XOR B XOR C. So if you see the sum expression, it is equivalent to a 3-input XOR gate. Similarly, we can select the carry outputs to write the sum of products. So for carry, so these are the rows which has high outputs. So for the first term, the product term is A bar B C. Next A B bar C. Next A B C bar. And for the final one, A B C. So if you simplify this, we are getting. So by grouping the first two terms, in both the terms, C is common. If you take it outside, A bar B plus A B bar. In the last two terms, we are getting A B common. So C bar plus C. So we know that C bar plus C is 1 and A bar B plus A B bar is again an XOR gate. So we can write it as A XOR B into C plus AB. So this is the expression for the carry. So we have converted the truth table to the Boolean expression. So for the sum, we are getting the expression as A XOR B XOR C. For carry, we are getting the expression as A XOR B into C plus AB. So implementing this Boolean expression in designing the logic circuit, we are getting this. So we need 3 input XOR gate. Instead of using 3 input XOR gate, we are using only 2 input XOR gate. For the first input, we are first XOR gate, we are giving the input as A and B. The output of this XOR gate is given as the input to the next XOR gate. The second input of the second XOR gate is C. So the final output is S, where S is equal to A XOR B XOR C. So for carry, so carry expression is A XOR B into C plus AB. So from the first AND gate, we have taken the input as AB. So here the output is AB. For the second AND gate, we have taken the input from A XOR B and C. So here the output is A XOR B into C. So these two terms is logically sum. So we are using an OR gate. So the final output is carry is equal to A XOR B into C plus AB. So this is a full adder circuit which is used to add 3 bits. Next, we will see off subtractor. So off subtractor is a logic circuit which is used to subtract 2 bits. So here there are 2 inputs A and B and 2 outputs difference and borrow. This is the block diagram of off subtractor which consists of 2 inputs A and B and 2 outputs difference and borrow. So first we have to know the basic binary subtraction. So 0 minus 0 is 0, 0 minus 1 is, so we cannot subtract 0 minus 1, so we have to get borrow. So difference is 1 and borrow is 1. So 1 minus 0 is 1, 1 minus 1 is 0. So this is difference, this is borrow. So this is the basic binary subtraction rules. So if you want to subtract 0 minus 1, so 0 minus 1 is we have to get borrow from the next higher position. So it becomes 10, 10 minus 1 is 1 with borrow 1. So 1 minus 0 is 1. So this is 1 borrow. So now first we will start writing the truth table to convert the truth table into logic circuit. So since here there are 2 inputs, let us take the inputs as A and B. So since 2 inputs, there are 4 possible combinations 0, 0, 0, 1, 1, 0, 1, 1. So by applying the basic binary subtraction rule, 0 minus 0 is 0, 0 minus 1 is difference 1, borrow 1, 1 minus 0 is difference 1, borrow 0, 1 minus 1 is 0, 0. So next step is we have to convert this truth table into sum of product terms. So to convert this truth table to sum of product terms, we have to select the rows which has high outputs. So here for difference, we are having 2 outputs, high outputs. So the product term for the first output is A bar B, and the second output is A B bar. So the difference is A bar B plus A B bar. We know that A bar B plus A B bar is an XOR gate. So it is written as A XOR B. So next we have to write the expression for borrow. So we have to select the row which has high output. So the second row has high output for borrow. So borrow is equal to A bar B. So A bar B means we are using both 2 gates, NOT gate and AND gate. So now we have to implement this Boolean expressions into the logic circuit. Since we are having 2 inputs, difference is taken across an XOR gate output. So A and B is given an input to the XOR gate and the output is taken as difference which is equivalent to A XOR B. So for borrow, the inputs are A bar and B. So A is initially given to an input of a NOT gate. The output of the NOT gate is given to an AND gate. B is directly given to the input of the AND gate. The output of the AND gate gives the borrow expression which is equal to A bar B. So using this logic circuit, we can able to perform off subtraction. That means we can able to subtract 2 bits. Next we have to see full subtractor. Full subtractor means it is used to perform subtraction of 3 bits. Again, in this case, there are 3 inputs, A, B and C be the 3 inputs, and there are 2 outputs, difference and borrow. So if you see the block diagram, it is clearly seen there are 3 inputs and 2 outputs. But in this case, A and B are taken as a 2 significant input variables, and C is taken as a borrow from the next higher significant question. So for example, so we cannot subtract 0 from 1 from 0. So we have to get borrow here. So 10 minus 1 is 1. Here 0, 1. So again C. So here we are using borrow also. So we have to consider 3 inputs. So we are getting this borrow from the next higher significant position. So this borrow is taken as a C. So now we have to construct the truth table first. So since we are having 3 inputs, A, B, C, we are having 8 possible combinations. So we know that the rule is 2 power n, where n is the number of inputs. There are 3 inputs, so n is equal to 3. So 2 power 3 is 8. So from the truth table, we have to select the rows which has I output to write a sum of product expressions. So for the difference, second row, third row, fifth row and last row. So by combining these 4 product terms, we can able to write the sum of product expression for difference. For the first output, the product term is A bar, B bar, C, and for the second output, the expression is A bar, B, C bar. For the fifth output, A, B bar, C bar. For the last output, A, B, C. Again, we have to simplify this expression. So, if you combine the 2 inner terms, A bar, B plus A, B bar, the common term is C bar plus. So, if you consider these 2 terms, here C is common. So, A bar, B bar plus AB into C. So, A bar B plus AB bar is again it is an expression for A XOR B. And this is the expression for A XOR B bar C. So we know that let A XOR B is equal to M. So A XOR B, the bar becomes M bar. Substituting these 2 values in the above expression, we get M C bar plus M bar C. Again, this is an XOR expression in terms of M and C bar. So we can write it as M XOR C, where M is taken as A XOR B. So A XOR B XOR C. So again, the difference is equal to 3 input XOR gate. So next, we will write the Boolean expression for borrow. So for borrow, we have to consider these outputs because these outputs are high. So for the first output, the bar product term is A bar B bar C. For the second output, A bar B C bar. Next one is A bar B C. Finally, ABC. So again we have to simplify this expression. So if we consider this, we consider these two terms, A bar, B bar, C and ABC. So in both these expressions, C is common. So A bar, B bar, C plus AB into C plus the next two terms, A bar B is common. So we can take it as C bar plus B. We know that C bar plus A is 1 and this A bar B plus AB bar is equal to X naught. So this is the Boolean expression for borrow. So we have first written the truth table. From the truth table we have converted into sum of products and the sum of product expression is simplified. So for difference we are getting A XOR B XOR C. For borrow we are getting A XOR B bar C plus A bar B. So implementing this expression in the logic circuit, we have achieved this logic circuit for full subtractor. So again, instead of using 3 input XOR gate, we are using 2 XOR gates. So for the first XOR gate, the input is taken as A and B and the output of the first XOR gate is given as the input of the second XOR gate. The second input is taken as C. So finally in this second XOR gate output, we are achieved the difference equation which is equal to A XOR B XOR C. For borrow, we have to get A XOR B bar into C plus A bar B. So the first AND gate, we are given the input from A and B. A is given to the NOT gate. Output of the NOT gate is given to the AND gate. So here we are getting A bar B. So in the second case, in the second AND gate, we are getting AX into C. Finally, these two expressions are combined to give a borrow output. So using this circuit, we can able to perform full subtraction. That is, we can able to subtract 3 bits. Finally, we will see the parallel binary adder. Sometimes we have to perform addition of 4 bits. So we have to consider 4 bit numbers A0, A1, A2, A3, B0, B1, B2. So while adding these twos, we getting the sum outputs as S0, S1, S2, S3 and finally carry out. So for the first addition, for the first bit addition A0 and B0, we need only half adder, but if the carry is passed over from this lower significant bit to the next position, we have to use full adder. So for the remaining 3 positions, we have to use full adders. But for the first position, we have to use half adder. Instead of using half adder, for the first LSB bit also, we are using full adder by making this carry in as 0. So, in all times, for the first full adder, carry input is 0. So, we are giving the input as A0, B0 to the first full adder. The sum output is taken as S0. This carry output is given to the carry input of the second full adder. So here we are having 3 inputs A1, B1 and carry in. This full adder produced 2 outputs which is sum 1 and carry 1, and this carry 1 is passed over to the next full adder, and this if the carry is generated by this full adder, it is passed over to the next full adder. Finally, we are getting the carry out and 4 sum outputs. So this is the 4-bit parallel binary adder. This adder circuits, that is arithmetic circuits, are used in computers, digital circuits, ALU, calculators, and any digital systems. So thank you.